So in this problem, we have two blocks, A and B, with mass 30 kilogram and 50 kilogram respectively, connected by this weightless, frictionless pulley system, and they are released from rest. We need to determine their speeds and accelerations when block A has displaced downwards by 0.4 meter. We've seen this problem before, and we could use Newton's second law, set up the equations of motion to solve this problem. But since now we've learned the conservation of energy, and in this case, as you can tell, we have weightless, frictionless pulley system. Therefore, only during the motion of these two blocks, only weight forces are doing work, which is conservative force. Therefore, we can apply the conservation of energy and solve this problem. Again, this is a problem of dependent motion. So from what we've learned before, we've done this before. If we choose this to be our datum, and this is the position vector SA representing the position of block A, and this is the position vector SB representing the position of SB. Then the conclusion from what we've learned before is that SA plus 4SB equals to a constant length L. Okay, we've done this before, so I'm skipping all that step. So from there, you already remembered we can write VA plus 4 VB is 0, and also AA plus 4 AB is 0. That's all correct, but from here we also need to recognize that if, say, for the next during the next moment, position of A and B have both changed, therefore you will have an SA plus a delta SA. That's the new position. At the same time, you have SB plus delta SB. That's a new position for block B. And they still have to satisfy this equation that 4 times SB plus delta SB add to the new position of A still equals to the same constant length L. So if you take this second equation minus the first equation, the reason why I can do this is because you have to recognize that this equation is valid for any moment, for any instant. This relation is always satisfied. Therefore, for the new SA and the new SB, this equation also is always satisfied. Therefore, if I take equation number 2 minus equation number 1, I can get to a similar conclusion that delta SA plus 4 times delta SB also equal to 0, similar to these two. And that's important because here we have the block A has displaced by 0.4 meter downwards. Therefore, we can tell that delta SB is going to be negative 1/4 times 0.4, and that is 0.1 meter upwards. So we can tell the displacement of block B. So now we're ready to write our conservation of energy equation. So we have total T1 plus total U1. In this case, we only have gravitational potential energy equals to total T2 plus total U2. Only gravitational. Initially, both of them are released from rest, so this term is 0. For this term right here, you can recognize that A and B are not at the same level, but that's okay. We can choose their respective initial position to be datum. Therefore, we can choose the initial position of A to be its own datum and initial position of SB to be its own datum. So if I choose that way, for this initial state, this simply equals to 0 as well. And then on the right hand side, total T2 equals to 1/2 MA VA 2 squared plus 1/2 MB VB 2 squared. Now don't forget VA and VB are related. Therefore, depending on which one you want to use, I'm going to use VB. Therefore, I can rewrite VA squared to be negative 4 VB squared, VB right here. So this right here is rewritten in this. Okay. And then for U2G, because I have chosen the initial position of A for its own as its own datum, therefore at final state, block A has displaced down by 0.4 meter. But block B, as we determined, has moved up by 0.1 meter. Therefore, U2G for A is going to be a negative value. It's weight times negative 0.4 meter. But for block B, it's going to be positive 0.1 times its weight. So now we're ready to write the equation. On the left-hand side, we have a big 0. On the right-hand side, we have 1/2 MA, which is 30, times not VA, but negative 4 VB2 squared. We are able to do this because of our previous knowledge of dependent motion. Plus 1/2 MB, which is 50 times VB2 squared. And then for U2G for A, that's negative 30 times 9.81 times 0.4 meter, because it replaced downwards 0.4 meter from its own datum. And then for block B, that is a positive 50 times 9.81 times 0.1, because it's moved up by 0.1 meter. So if you have doubts about choosing different datum, don't forget, it is really the displacement of the individual block that matters. So as long as you're comparing A to A, B to B, so comparing A to its own datum, B to its own datum, then you'll be fine. So as you can see from this equation, we only have one unknown, which is VB2. So from here, we can solve for VB2, which is the final speed of block B, and that is going to be 0.509 meter per second going up, and VA2, which equals to negative 4 times VB2, that's negative 2.04 meter per second going down. So that answers this question right here for their speeds. But what about their acceleration? Because during this process, weight is the only force doing work, and the weight of block A or block B is a constant. Therefore, we can deduce that the acceleration of block A and B are going to be constants as well. Therefore, now you have a problem with kinematic problem with constant acceleration. So we can call this equation V squared equals to VO squared plus 2 times AC constant acceleration S minus SO, if you remember this equation. So for B, we have, so if we solving for B, we have 0.509 squared equals to initial velocity is 0 plus 2 times a B, that's a constant acceleration for B, times the final position is 0.1 meter minus 0. So from here we can solve for AB. Constant AB equals to 1.30 meter per second squared. And don't forget, we have this relation that AA also equals to negative 4 AB. Therefore, from here, AA equals to negative 5.18 meter per second squared downwards. You can try to solve this problem using Newton's second law, equations of motion, and you should be able to get the same results.